Hi, I am Tom Thompson, W0IVJ. I've been doing some experiments with differential and common mode currents. I'd like to share with you some of the results. Here's the setup that I used. I have a 10 megahertz signal generator going through a 4-to-1 transformer, so it transfers 50 ohms to 200 ohms here. I have a differential current sensor on one line and on the other line, and a common mode sensor on the twisted pair. This is a 3-foot twisted pair transmission line. I also have a common mode injector where I can inject 9.6 megahertz of common mode current. This sensor right here is displayed on channel 1 of the oscilloscope, this one on channel 2 of the oscilloscope, and then the common mode current goes through a splitter and goes to a spectrum analyzer and channel 3 of the oscilloscope. I have switches, switch 1, switch 2, and switch 3. By switching switch 1 or switch 2, I can unbalance the balance line and cause a common mode current to flow. The differential currents flow in opposite directions. The common mode current flows in the same direction, but they're all in the same circuit. Here are some photographs of the various transformers. This is T1 that converts the single-ended to a signal to a differential signal. These are the two T2 and T3. These are the two sampling cores that sample the differential currents. This core right here is T4. It samples the common mode, and this core right here enables me to inject some common mode current. In this photograph, there's all the switches are open. So this is a scope display of channel 1, channel 2, and channel 3. You can see that the currents, the differential currents, are of equal amplitude and out of phase, and there's very little common mode current showing here. There's actually a little bit of common mode current that is inherent in the imbalance of the transmission line that exists because it's not completely balanced, and that's at minus 66 dBm. Here I've closed switch 1. That induces a common mode current, and you can see that the differential currents now are very unbalanced, and the common mode current signal is present. The common mode current now went up from minus 66 to minus 20 dBm, so we've got a 46 dB increase in common mode current. Similarly, if I close switch 2, I get the same amount of common mode current created, and the phase and the amplitude now have changed between the two differential signals. I'll switch back and forth so you can see this. You can see right here, this one is larger than this one. And now then, this signal is larger than this one, and the phase is shifted. If I close switch 3, leaving switch 1 and switch 2 open, you can see the minus 86 dBm injected current, common mode current, appearing on both traces of the differential. You can see it a little bit right here, and you can see it a little bit right here. If I close switch 1, now you can see that the common mode current has increased here and here, both of them, And you can also see that it mostly appears on switch 1. If I close switch 2 with switch 3 still closed, I get the same appearance on the oscilloscope, but now you can see the common mode current appearing on the other line. Here I've closed switch 1 just as a reminder, and you can see that this is at minus 42 dBm, and this one is at minus 22 dBm. Now I've inserted a common mode choke. Here's the common mode choke right here. It's 43 material, 5 turns on a ferrite 26431/01902 core. The choking impedance was measured at 2800 ohms at 10 megahertz. And you can see that now the differential currents look very much balanced and out of phase like they did initially. And you can see that the common mode current here has been greatly reduced. And we went from minus 20 to minus 50 dBm, so there was about a 30 dB decrease due to the common mode choke. I'll go back and forth so you can look at this. There's without the common mode choke, with the common mode choke, without the common mode choke, and with the common mode choke. So here is a illustration of what the common mode choke did. This is the common mode current without the choke. Here's the common mode current with the choke. And you can see that there has been a 30 dB decrease in common mode current, and the differential currents have more or less been restored to their initial state. So in conclusion, we see that a balanced transmission line has equal amplitude and opposite phase signals in each line and very little common mode current. Upsetting the balance introduces a common mode current and causes amplitude imbalance and phase shift in the differential currents. However, a common mode choke of sufficient impedance can restore the differential currents to close to their previous amplitude and phase status.